everyone, this video is on the topic of linear approximations found in section 14.4 of our text. Recall that in our last video we talked about tangent planes. We can see a surface here in blue with its tangent plane sitting on top of it at the point P in yellow. And we said that we can think of this tangent plane to our surface at that point P as consisting of all possible tangent lines at P to curves that lie on S and happen to pass through P. So drawn in our tangent plane are two tangent lines at P, the tangent lines T1 and T2, but we could draw infinitely more tangent lines that also touch our surface at the point P. Now, if f has continuous partial derivatives, we saw that the equation of the tangent plane to the surface z equals f of xy at the point x naught, y naught, z naught was given by the formula here. Z minus z naught equals our partial derivative of f with respect to x evaluated at our point times x minus x naught plus our partial derivative of f with respect to y evaluated at our point times y minus y naught. And furthermore, we saw that the tangent plane at P is the plane that most closely approximates our surface near the point P. We had this example with the elliptic paraboloid z equals 2x squared plus y squared, and saw that as we zoom in on that point of tangent C, our surface more closely and closely resembles that plane. It becomes very difficult to tell the difference between the surface and the plane if we really zoom in at that point of tangent C. And this leads us to the idea of linearization. So in our previous example, we saw that for this elliptic paraboloid, 2x squared plus y squared, that when we were near the point where xy was 1, 1, that our function was really close to its tangent plane, and we found the equation of its tangent plane to be 4x plus 2y minus 3. Now, this equation is sometimes called the linearization of our function. So I want to point out the linearization is the exact same thing as the tangent plane, because when we zoom in on that surface, it really looks like its tangent plane. Now, for example, this is telling us that if xy is the point 0.95, 1.1, to find the value of the function, we can evaluate its tangent plane or its linearization at the point 0.95, 1.1, and see that there our function should be really close to the value 3. In fact, the actual value of the function at that point is 3.015. So we got a pretty nice approximation using that tangent plane. However, it was important that the point we were interested in, the 0.95, 1.1, was really close to the point of tangency we worked with initially, that 1, 1 value. Because if we move farther away to the point 2, 3, then at 2, 3, our linearization, our tangent plane, gives us the value 11, whereas the actual value of the function is 17. So it's no longer a good approximation because 2, 3 is just too far away from that initial point of tangency at 1, 1. So here's our formula for the linearization. If f has continuous partial derivatives, then the linearization or linear approximation of our surface at the point P is given by our function is approximately our partial derivative of f with respect to x evaluated at the point times x minus x naught, plus the partial derivative of f with respect to y evaluated at the point times y minus y naught, plus the value of the function at that point, f of x naught, y naught. Now, when we compare this to our equation of the plane, again, I want you to notice they are exactly the same thing. We've just taken that z naught value and added it to the other side of the equation. So the tangent plane and the linearization are the exact same thing. Let's do an example. Let's find the linear approximation of the function natural log of x minus 3y at the point 7, 2 and use it to approximate the value of the function at 6.9, 2.06. Here we go. So our function is the natural log of x minus 3y. The first thing we want to do is to compute the partial derivatives of this function. So the partial derivative of f with respect to x is 1 over x minus 3y. And the partial derivative of f with respect to y, we would do 1 over x minus 3y times negative 3. We're now going to evaluate these partial derivatives at the point of tangency we're interested in, so the point 7, 2. And at that point, our partial derivative of f with respect to x is 1, and our partial derivative of f with respect to y is negative 3. Here is our equation of the tangent plane. So we're going to plug in our points. Notice that if we evaluate the function at 7, 2, we get the natural log of 1, which is 0. And of course, our x naught, y naught were the points 7, 2. And then we include our partial derivatives evaluated at our point, so 1, negative 3. So our tangent plane becomes z equals x minus 3y minus 1. Now you may be thinking, this problem didn't ask for the tangent plane. It asked for the linear approximation, right? But remember, those are the same thing. So since the tangent plane at 7, 2 is x minus 3y minus 1, then we know that near that point of tangency 7, 2, our function most closely resembles the plane x minus 3y minus 1. And so we can approximate our function at 6.9, 2.06 by evaluating our tangent plane at that point. So we see that our function is approximately negative 0.28. And when it's possible, it's always nice to double check that our answer seems reasonable. So you can find the actual value of the function by plugging into that natural log equation. And we see that the actual value of the function is approximately negative 0.3285. So our answer seems reasonable. Now, a natural question that my students always have is, why would we approximate the function using a plane when we could find the actual value simply by plugging into the equation? And that is a great question. So to help us see the value of these linear approximations, I want to do one final example. Here is an example that is familiar to us if you've been following these videos, where we have a chart of wave heights in the open sea, dependent on the speed of the wind and the length of time that the wind has been blowing at that speed. Now, the reason why this is a great illustration of linear approximations is because we do not have an equation. We only have data values that have been recorded. So what if we want to approximate a different value, a value that's not in our chart? For that, we can use this topic of linear approximations. Let's see how it's going to work. We want to use the table to find a linear approximation to the wave heights when the wind speed is near 40 knots and the wind has been blowing for nearly 15 hours, and then estimate the wave heights when the wind has been blowing for 14 hours at 43 knots. Now I'll go back to the table in a minute, but you'll see that the value for V equals 14, T equals 43 is not on our chart. So this is the power of using linear approximations. We'll use the data points that we know to approximate a data point that we want to know. Okay, so we need a linear approximation when V is 40 and T is 15. So let's go back to our chart. And we see that when V is 40 and T is 15, the wave heights there are 25. So we're going to need that data point momentarily. Here we go. Now, we worked with this example back in section 14.3 when we talked about partial derivatives, and we found that the partial derivative of f with respect to V at 40/15 was approximately 1, and the partial derivative of f with respect to t at 40/15 was approximately 0.7. So if you're curious where those values came from, go back and re-watch that video. Now, from the table, we found that the actual value of 40/15 was 25. So, We're now ready to use our formula for the linear approximation. We plug in our point values of 40, 15, and 25, and our approximations for our partial derivatives of 1 and 0.7. So when we clean it all up, we get this nice linear approximation that our function is approximately v minus 40 plus 0.7 times t minus 15 plus 25. And so we can then approximate the value of the function at 4314 by replacing v with 43 and t with 14. So we get a value of 27.3. And this tells us that when a 53 knot wind has been blowing for 14 hours, that the wave heights are approximately 27 feet. So we were able to use linear approximations to give us an approximate value for a function where all we had was data points instead of an actual equation. Great. Thanks, guys. Bye.